it's rare. We do have an example in the notes where we can guess at the number of clusters. Maybe you're in a situation where you can guess the number of clusters. If so, that's really good. But most of the time, you're doing the exploratory, you're trying to decide if there's clusters in the data. It's super challenging. Yeah, there are lots, because you can use all the different distance measures and you can do it basically forwards and back. There's so many choices. There's a lot of them. But there are some that are more popular than others, and I'll talk some about those. Yeah, lots of them. Hierarchical methods build clusters from smaller clusters. Partitioning methods to start with a big cluster and try to divide it up. And we'll talk about those. The one that Bill and I put in the notes is called nearest neighbor. And nearest neighbor is, I don't know if it's the most popular hierarchical method. It's a pretty popular hierarchical method, but it has various flaws that we'll discuss. Yeah. So, if you're in hierarchical clustering, the is building up from a whole bunch of clusters into, in the end, you have one cluster. So you don't, in hierarchical clustering, you don't have to choose the number of clusters, which makes it very popular. Because most of the time you don't know how many clusters you have. We join together clusters. I'll talk about how that works. The agglomerative is joining them together. And divisive is splitting them apart. You start with one big cluster and then you split it in two. And then you take those two clusters and you split them into more clusters. 95% of the time, people do agglomerative clustering. You start with all the points in their own cluster. So you're not simplifying the data at all. In the example that's coming up, I think we have 6 points. And we start with each of them in their own cluster. In some sense, that's perfect clustering. Everybody's right at the mean of their group, but that's not a very interesting clustering. Divisive starts with all the points in the same group, and it doesn't get used very often, so I do use it sometimes to see if I get the same answer that I get with an agglomerative approach. So the way nearest neighbor works, and all the methods of agglomerative clustering are similar. They just use a different measure of distance. And we'll talk about what those are at some future slide. Unfortunately, different fields give different names to the nearest neighbor method. Who calls it nearest neighbor? I don't know. Other people call it single linkage. I don't know how to differentiate who calls it what, but there are multiple names. Just remember that there's a distance measure involved in the cluster analysis, and you darn well better know what it is. And you kind of want to know the properties of that distance measure. You start with all the points in their own cluster, which is, no matter what distance measure you're using, there's only one point in each cluster. Every point themselves, and so that the distance measure is equal to 0. But then you start joining them together. And once you join 2 points together, they sort of become 1 point in the cluster analysis world. And think of the new cluster as a point, and define the distance from any point, which is a group of points, right, when you get to here, as the minimum distance to any point in it, if you're doing nearest neighbor. So nearest neighbor is, there's a reason why it's called nearest neighbor. I have no idea. The genetic people probably use linkage, because linkage matters in genetics. But if you're trying to, if one of them is, so what's the distance between this point and that group? Nearest neighbor says the distance is equal to this. Time for the rig. That's the distance. Furthest neighbor says the distance is between this one and that point, because that's the furthest one away in that group. Average linkage, and oh boy, what's the linkage name for furthest neighbor is, I'll remember in a second. Average linkage is the distance, the average distance between the points in there. So average distance says the distance is this, and furthest neighbor says the distance is this. Which one's right? There's no right. They're different distance measures. They have different properties, and they get different answers sometimes. But if you really have P clusters in the data, they're all going to get this. They're going to get it right. It doesn't matter which one you use. It's when there's borderline stuff that they start to get different answers. So we have 6 points, and how do you go? This is an example of what the software is doing, just in a lot more dimensions and a lot more computation. But basically, this is the game that's being played. 6 points. The example doesn't tell you the dimension of the points. It doesn't matter, the dimension of the points doesn't matter how many variables you have. All that matters is that you have 6 points, and we're going to start grouping them together. Well, if we have a way of deciding how far apart they are, like the nearest neighbor method, then we can measure the distance between point 1 and point 1. By the way, there's a 0 right there that's not there. The distance between a point itself is 0 by all the measures. If your distance measure didn't have that property, that'd be a very interesting measure of distance. In fact, I don't think there's probably an axiom that says distance between a point in itself has to be 0. I would hope. I don't think you can prove that, by the way. The distance between point 1 and point 2 is 0.31 units. Great. The distance between point 1 and point 3 is 0.23 units. So the computer can do this. It can calculate the distance between all the points. And when all the points are in separate clusters, no matter what, the overall measure of the clustering, that's not the right terminology, is 0. We'll talk about how we measure that in a second. So the first step is that in an agglomerative approach, this is the joining together of the points. The first thing that's going to happen is that 0.3 and 0.5, because they're only 0.04 units apart, get joined together. And so we have some, if I had a two-dimensional situation. 1, 2, 3, 4, 5, 6. Which 2 points are close? So they all start in the same cluster. Which 2 are closest together? Well, it turns out that points 3 and 4 are closest together, and by my picture, it's going to be those 2. So the first step of the cluster analysis is points 3 and 4 get joined together because they're close, or in the 3 and 5, because they're the closest. But now you don't have 6 clusters anymore, you have 5 clusters. And now you have these 2 got joined together. And so basically we have 5 points, or 5 clusters. I'd rather call them clusters. What's going to happen next? Well, now we have to redefine the distance between 3 and 5 and the others, because it's not the same as the distance up there. A bunch of the distances are the same. So the computer scientists, by the way, will remember these distances and not recompute them, because they're all concerned about doing this quickly. So now we're down to those 5 clusters, and we need the distance measurement. Well, the distance between cluster 3,5 and cluster 3,5 is still 0, but the difference is, so that point 3,1 should be on my previous slide. You guys can. The distance between 1 and 2 is 0.31 in both steps. 1 and 2 is 0.31. Good. We didn't make the slide wrong. It's not changing, but what is changing